Before we make any attempts to improve performance, let's do some quick analysis. Our problem is that we have too many flights in the test data that are delayed that are not being predicted as delayed. We need to determine a way to increase the accuracy of our predictions. What are our options for improving the accuracy of our predictions? Remember when we went over the workflow, we discussed these options at a high level. We could go back to the prepared data and get additional data, or we could select a new algorithm that worked better with our data, or retrain the model with different parameters that could improve the performance. This updating and performing previous workflow steps is very common in machine learning. Let's see how these options translate into changes we can make in our problem's workflow. For our solution, revisiting workflow steps would map to the following options. The simplest form of getting additional data means adding additional predictor columns from our existing data. The most obvious column, and one that will definitely improve performance, is departure delay 15. But think about that for a second. While it is true if your flight leaves late, it is likely to arrive late, is this a practical feature for what we want to predict? You can only detect if a flight is going to leave late a little bit before it departs. So how useful is that? It is likely that using delay departure as a feature for predicting if a flight is going to have delayed arrival is not useful in that many usages of the model. The second option would be trying to adjust the training settings, but I spent a while doing this and the improvements were pretty subtle. Notice that the problem is with unpredicted delay. Are there algorithms that could do better in this area? This is an area where ensemble algorithms can be useful. Let's try random forest. Random forest is an ensemble algorithm that creates multiple trees and uses a technique called bagging to improve predictive performance. We can determine if the random forest has improved performance by checking the number of unpredicted delays and the resulting specificity value. We need to first load the random forest library. Then we need to train a model with the random forest algorithm. We'll only use a couple of the algorithm's many options. And to make things interesting, let's not use caret's train method. Rather, let's see the raw random forest constructor so we can see what caret hides and standardizes. The train data filter -1 is R's way of creating a new data frame which excludes the first column, which in our data happens to be arrival delay 15. The next parameter is the column to predict for, namely arrival delay 15. The last two parameters tell the random forest algorithm that we care about proximity and that the algorithm should use the importance of each feature in creating the trees. We press the return key and the algorithm processes the data to create a trained model, and we wait for a long time. I sped up this screen. The actual training time was around 8 minutes versus the 5 seconds for the logistics regression. As we discussed earlier, trees can take some time to train, and the multiple trees used by this ensemble algorithm take even longer. Now let's use the new random forest model to predict which flights in the test data will be delayed. Finally, let's evaluate the performance of the model by looking at the confusion matrix. Looking at the matrix, we see there are 1,938 delays in the test data. With the random forest algorithm, we predicted 229 of these, which is much better than the 31 we predicted with logistics regression. And this difference boosted the specificity from 0.016 to 0.1182 over 7 times. But there is still room for more improvement. So what can we try now? We could try to further improve the performance by adjusting some of the parameters in the random forest, looking at doing some pre-processing of the data, or perhaps trying other algorithms. After each of these changes, we would repeat the training and evaluating the results as before. But perhaps there is another option, rethinking about the problem. What do we know about flights? As we mentioned earlier, flights that depart late will almost always arrive late. So what causes a flight departure to be delayed? Do we know? Perhaps a little subject knowledge is required. If we read through the information on the DOT site, we see that weather is a significant cause of delays. So maybe we should add weather data. Where would we go in the machine learning workflow to determine which weather data to add and how to add that data? Well, we are back at preparing data. All set for another cycle of the workflow with the addition of weather data. We would first clean and mold the weather and flight data. Then we would follow on to the subsequent workflow steps of selecting the algorithm, training it, and finally reevaluating the performance of the new model with the new data. But because this is an introductory course, and we have done these steps before, let's leave getting and preparing weather data and incorporating it into flight data to another time, or perhaps as an exercise for you to try. You have seen these steps before, so you know what to do and how to do it. But for right now, let's recap performance improvement. We have seen that our efforts are making improvements in the performance of our prediction model, and for each cycle of changing the data, settings, and/or algorithms, we'll hopefully see more performance improvements. But these improvements can take some effort to yield results, so we need to weigh these efforts against the results and make a decision on how much performance is good enough. It seems like sometimes the hardest thing with machine learning is determining when to stop cycling through the machine learning workflow in search of better performance. In this module, we evaluated the performance of our trained model against test data. We did this by using the predict function to generate a prediction of how well the model predicts if a flight will be delayed. We used the confusion matrix function to review the prediction performance of the model and inform us of areas that needed improvement. We chose to improve the performance by using a different algorithm, random forest. Changing the algorithm improved performance substantially, but as always, there was room for further improvement. Finally, we revisited the problem and used some domain expertise and reasoned that weather data would be useful in a future effort to improve the prediction of whether a flight would be delayed. In the next module, we will summarize this course and go over some additional information that will be helpful in your machine learning journey. See you there.